Achha, so this one is W18 question paper 4.2. ठीक starting with the first question. He's saying an alkene, a carboxylic acid, and a ketone, all of similar volatility are mixed together. The mixture is then analyzed by gas chromatography. So I'll explain what gas chromatography is. And the diagram is this one. So I'll just quickly give you a very brief overview. Chromatography is very simple. It's just 2 lines. The different types of chromatographies. What happens in a gas liquid chromatography is this is what happens, that you have, let's say you have a tube-like structure. That's a long cylindrical tube-like structure. And let me draw this properly. So this is a long cylindrical pipe, and it has a particular solvent. Now that solvent is your stationary phase. Let me come to that. Let me just quickly draw this. So this particular tube-like structure has a solvent in it. So it is lined with a solvent. And that solvent could be any solvent. It could be any solvent. It could be a polar solvent. It could be a non-polar solvent. It could be water. It could be CCl4. It could be any sort of liquid. And that is considered your stationary phase. Stationary phase means that it would not really be moving that much. And then there is a gas that is passed through this tube. The gas is usually an inert gas. And since it is an inert gas, it's going to be a noble gas. And that's your mobile phase. Okay, so if you remember your O-level stuff, you had, I'll come to the O-level stuff as well. But there's a mobile phase and there is a stationary phase. And now in the mobile phase, in this gaseous phase over here, a vaporized substance is added, and it's going to be a mixture. Let's say it's a bunch of dyes. There's a bunch of colored dyes. Some of them are some of them. One second. So there's a black dye and there's a green dye, and it's been vaporized, and that is pushed into at high pressures, is pushed into this tube-like structure. Now, Suhail, aapka wo mic on. So that is pushed into the tube-like structure. Now, what will happen is, like if I draw a section of this tube-like structure, what's going to happen is, so remember, think of this as a magnified version of the tube. Now the tube has a stationary liquid that's coating it. And here are your vapors. This is your green vapor, and there's your black vaporized dye that's passing through it. Now what's going to happen is, one of the dyes is going to be soluble in the stationary phase, and one of them is going to be less soluble. So there's going to be a difference in solubility of the substance. So let's assume, okay, this black dye over here, okay, let's assume that this black dye over here is very soluble in the, so I'm going to pick it, and it mixes into the stationary phase, which is the solvent that is, or the liquid that's surrounding or coating the tube. So what will happen is that the black dye would slow down. It will slow down, while the green dyes over here will continue to move with the gas. They'll continue to move forward. They'll continue to move forward, while the black dye is going to slow down because it's more soluble. It's more soluble in the stationary phase. So it's going to slow down. So over here at this end, so let's assume, do you get this point? Is this point clear to everyone? Okay, how separation is happening? Is this clear? ये clear Zainab?
जी सर.
ठीक है. Alicia, is this clear? Sam, is this clear?
Yes, sir.
Okay, so
Yes, sir.
so that's the simple idea. Okay, it's just very keep things very basic. It's just a simple concept, and the simple idea is that they're going to ask you why separation happens. It happens because of partition, which is that there is a difference in the solubility of the substance. So this is something that they will ask you. That what is the concept behind separation? Why are the dyes separating? So there's a difference in the solubility of the vapor, of the mixture, in the mobile and stationary phase. Because that is often referred to as, the concept is referred to as partition. Now remember, the black dye is not going to remain there forever. What will eventually happen is that at some point the black dye would vaporize again. And I'm not able to pick this up, but 1 second. So at a certain point, the black dye would vaporize again, but it will slow down. The green dye would be much further ahead compared to the black dye. So for the black dye, it's going to take a much longer time. So if I draw the output, what do you get over here? At the opposite end, at the output, you're going to get the green dye first. So this is going to be, so the green vapor or green dye would be obtained first because it's traveling faster. The black dye is slowing down. So the black dye or its vapor would be obtained much later. And right at the beginning, the first thing that you're going to get initially is the solvent. The very first thing that you're going to get is the stationary phase. Why? Because some of the solvent would be leaking out of the tube. Like if you're passing the gas or vapor at high pressures through these tubes, the first thing that you'll get is the solvent itself. Some of the solvent is going to get pushed out initially. The vapors are going to come out much later. So that's the basic idea of what a gas liquid chromatography is. Okay, so that's gas liquid chromatography. Is this clear to everyone?
Sir, can you explain the last point again?
ये वाला solvent वाला? मैं बता देता हूँ, I'll explain. Is this point clear that the dye that is not soluble or the vapor or whatever the mixture is, if it's not soluble in the liquid, it will travel much quicker through the tube and you'll obtain that first. So the green vapor, I'm just assuming that the green vapor is not dissolving in the solvent, so it will appear first. In the tube pinner, you'll detect it. This is the time axis. So you're going to detect it much earlier. And the black vapor, because it's constantly dissolving in the stationary phase, and then evaporating, then dissolving back again, then evaporating. So it's going to take a much longer time to travel through the tube. So the black vapor would be obtained at a much later time. Like right at the beginning, I said the first thing that you'll get out of this tube is the solvent. It's the stationary phase, because some of the solvent would be leaking out of the tube. So even if there is no green vapor or black vapor obtained, the first thing that you're going to get out of this tube is the solvent that would be, there was solvent that was lining the tubes, and that is the first thing that you'll obtain as an observer at the other end. Okay, is that point clear?
Yes, sir.
So coming back to this question, so you've got these three things. He's saying an alkene, a carboxylic acid, and a ketone, all of similar volatility. Similar volatility means that they evaporate, almost have the same boiling points. So they have the same tendency to form vapor or get vaporized. The mixture is analyzed by gas-liquid chromatography. The separation of the three compounds depends on their relative solubilities in the liquid and stationary phase. Liquid stationary phase is an alkane. So what he's saying is, the tube that you have, the liquid that is lining the tube is an alkane. So the first thing is alkane polar or non-polar? Okay, what type of intermolecular forces does it have? Saim, kya hoga? What's Ibrar? Is it polar, non-polar?
Non-polar.
So it's non-polar. And the rule is that non-polar dissolves non-polar, right? And polar dissolves polar. So that's your stationary phase. And that is the thing that will slow down the vapor. Okay? So mixture of carboxylic acid, alkene, and ketone, they're all traveling through the, so you've got all three things. So there's a mixture of, let's say this is alkene. This one is ketone, and the other one is a carboxylic acid. So the orange one is the carboxylic acid. So they are all being pushed by a mobile phase, which is the inert helium gas or any noble gas. Did he tell us which? He didn't mention the gas, but there's a gas that's pressure at high pressures that's pushing the vapor through the tube. So which one will dissolve in the alkane? The one that will dissolve in the alkane first is the non-polar one, which is, it's going to be the alkene. So the alkene, so L over here is going to be alkene. It's going to be alkene. Why? Because it's non-polar. So what will happen to it? It will dissolve very frequently in the stationary phase. So it would take a much longer time for it to move through the tube. And the first one to reach the least amount of time that would be taken would be taken by J. And J would be carboxylic acid. Why? Because carboxylic acid is highly, so this one would be carboxylic acid. Because it doesn't mix with because it's polar, it does not mix with the alkane, which is the stationary phase. Is the idea clear? You clear, Munir? Is this clear? Sam, Nadine?
Yes, sir.
So then you have the next one is, one second.
Okay.
Sir, how do you know कि J हमारे पास acid और L is an alkane?
No, I said it's taking L is taking the longest time. So why is it taking the longest time? Because it's constantly dissolving in the stationary phase. Is that idea clear?
Yeah, okay.
So my other point, L is taking the longest time. That means L, and he said that the stationary phase is an alkane. Alkane dissolves which one? Non-polar, right? So he gave you three things, that there were a mixture of three things that's passing through this tube. So which one would be taking the longest time? It's going to be the alkene, because the alkene would constantly dissolve in the alkane. Is that point clear? Okay. The alkene, instead of moving forward, it would constantly dissolve in the alkane. So that will slow it down, while the other particles would continue to move forward. Ibrahim, is this clear?
G, yes.
And carboxylic acid is going to take the shortest time to move through the tube. Why? Because a carboxylic acid forms hydrogen bonds and alkane does not form hydrogen bonds. So whatever liquid is lining this tube, the carboxylic acid will not mix with that and it will continue to move forward. So the explanation would be just as simple. It's always going to be this type of question. I mean, you don't have a lot of variety of questions in this. The questions in gas liquid chromatography are going to be kind of very straightforward. So complete the table. So we've already identified that, and the explanation would be that nonpolar dissolves nonpolar. So alkenes and alkanes have van der Waals forces, and carboxylic acid is polar, so it does not mix with an alkane since it's nonpolar. So I'll also open a. Which paper is this? 1 second. I'll open a marking scheme next to it. That's the first one. So you've got, I mean, it's just the whole thing, polar. So he just gave a one-word explanation, which was most polar. We wrote further explanation, which was that polar dissolves polar. So moving to the next question. The next question is, a student calculates the area underneath the 3 peaks in the chromatogram. The area underneath each peak is proportional to the mass of the respective compound. Calculate the percentage by mass in the original mixture of the compound responsible for peak K. So calculate the percentage by mass. So he's pretty much given you everything. He's saying that the area under each peak is proportional to the mass of the respective compound. So you had these 3 peaks. So it is pretty obvious that more of J's, the amount of J that is being obtained at the end is much bigger compared to the amount of K. And he has already given you the areas of the peaks. So all you have to do now is, and he's also told you that the area underneath each peak is proportional to the mass. So he's asking you to calculate the percentage by mass in the original sample. So the original sample consists of all 3 things. So what is the percentage by mass of K? That would be 18 divided by 46 plus 18 plus 28, and you multiply it by 100. So what do you get for this? Does anyone have a calculator? Munir, what are you getting for this?
19.56.
So that's 19.56. So it's percent. That's the amount of K. Moving to the next question, that's a substitution reaction. Write an equation to show how AlCl3 generates the electrophile needed in this reaction. So how does AlCl3 generate the electrophile? For this,
Polarizing the bond.
Yeah.
Attracting by polarizing chlorine molecule by attracting.
But at the moment, he's also asking for the equation that, like, you had AlCl3, right? So the way it did was that the electrons over here would get repelled because of the benzene electron cloud, but benzene's electron density wasn't very high. So the polarization was weak. So what would happen is that Al from the other side would attract one of the Cls and the polarization would increase. So the positive Cl would become more positive and it would attract. So he's asking, write an equation to show how the AlCl3 generates the electrophile. So he's only asking about this equation. So what AlCl3 does is, so you just have to write an equation for that part of the mechanism. So you have an AlCl3 molecule. The AlCl3 grabs one of the Cl ions. It becomes AlCl4 with a charge of -1. And the other one is now Cl +1. That Cl +1 goes and attaches itself to the benzene. So draw the mechanism of this reaction. between this. So we remember this one, we just wrote the equation for this part, how the electrophile was created in the first place. And include all relevant curly arrows. So you have to draw the mechanism. The mechanism is, I mean, we already did part of it. That's the first step. What's the next step? The next step is AlCl4 -1 is produced, and the benzene now has one of the Cl positive goes and attaches to the benzene. So the electron cloud is now partial. And in the next step, what happens is that the it loses its electron and leaves. And you can bring in the AlCl4 in that as well. So include all relevant curly arrows. We can just have a quick look at the market scheme as well. So that's the last step. This is the middle part. That's the first step. And then I said this one, I'm not sure, but they actually continued from that point forward. I think this one is way better. I mean, this is the actual one, but I think they divided it into steps. So they started with Cl+1, but I'm sure this one would be fine as well. So the next step, H leaves. And write an equation to show how the catalyst is regenerated. So the catalyst is regenerated that you have AlCl4 -1. The H is lost and the H+1 comes and grabs one of the Cl's back again, and it ends up forming AlCl3 back again. So the only thing that he's doing in this reaction is that he's broken it up into different steps. Okay, but is the question clear?
Yes, sir.
Yes, sir.
So just for revision, we can have this open as well. That remember electrophilic substitution. You have nitration and you have bromination and chlorination. So let's move to the next one. Explain what is meant by a homogeneous catalyst. That's easy. That same phase. The catalyst has the same phase as the reactants. Next one, complete the table by placing one tick in each row to indicate the mode of action of the catalyst. So rhodium in the removal of NO2 from exhaust gases, that's a solid. These are gases, so that's definitely heterogeneous. Different. This is catalytic converter. I mean, this one over here is the catalytic converter, where you have either platinum or palladium or rhodium catalyst, and it removes the NO2 gases. So that's a different phase. This one is an example of a homogeneous catalyst where all of them are ions. The catalyst is an ion, and whatever the reaction that's happening, those are also ions. Next one is about transition metals. So complete the diagram. Remember, copper is that special case. It has 29 electrons. But if you write the electronic configuration for 29, it's going to be 3s2 3p6. And then it should be the 3d fills after the 4s. It should have been this one, 3d9 and 4s2, but instead, the completely filled configuration is more stable. So it's actually 3d10, 4s1. So copper is actually 3d10 and 4s1. And copper 2+ would be that 2 electrons would be lost from the outermost shell. So it's now going to be having an incomplete subshell. Explain what is meant by the term degenerate in this context. So degenerate means orbitals having the same energy level in a particular subshell. So having the same energy level. So for example, Px, Py, and Pz are exactly, they're exactly the same orbitals, except that the orientation is different. Similarly, all the d subshells, they are degenerate. They all have the same energy level. Now, complete the diagram to describe the splitting of the 3D orbital. I'll just open the notes. What happens is that you have Vulcan notes. It will have diagrams. Just a second. Okay, I've sent you the transition metal notes. Remember, every time the question is going to be exactly the same. 1 second. Yes. So why are transition metals colored? They're colored because, so where's the D subshell? Now, let me just show you the D subshell. So here's your D subshell. It's a degenerate sub. All orbitals are degenerate. They have exactly the same energy level. But what happens is, once a complex is formed, once a complex is formed, the lone pairs of the ligands that are now coming in and sticking to the metal line, the lone pairs, they cause repulsion. So some of the d orbitals are between the axis, some of them are on the axis. And what happens is, once a complex is formed, in some of the d orbitals, it becomes harder to keep electrons. In other ones, it becomes easier to keep electrons because of the repulsion factor that is coming in from the lone pairs on the ligands. So in this case, for example, in the pink ones between the axes, it's easier to keep electrons. In the green ones, it's harder to keep electrons. So your D subshell, it splits into two energy levels. And that is what causes colors of compounds as well. So he's talking about the octahedral complex. The octahedral complex is specifically this one, where all the water molecules are approaching on the axis. So it becomes harder to keep electrons in those orbitals that lie on the axis, the 3D x square minus y square and the 3D z square. So this is exactly what he's asking for. Okay, how is it splitting? So two of them, they go at a higher energy level, and three of them. So this one is 3D x square minus y square. And this one over here is 3D z square, while this one over here is 3D xy, they're between the axis. 3D xz, 3D yz. So complete a diagram, describe the splitting. So we just did that. And then he's asking, what is meant by the term bidentate? And this is a bidentate ligand. So this is what it means. Somewhere, kahan pe kiya tha? So this one. A bidentate ligand is a ligand that is capable of forming two dative bonds. The metal line is the same, but it's got lone pairs at either end of the molecule. So one lone pair bonds or gets attracted to the copper ion from this side. One lone pair forms a dative bond from this side. So this one is a ligand with two lone pairs involved in forming coordinate bonds. That's a bidentate ligand. I'll just quickly check what the marking scheme answer is for this one. That donates two pairs of electrons. So that's kind of the same thing. A ligand with two lone pairs involved in forming, that's exactly the same thing actually. So that's what bidentate is. Monodentate is a ligand with one lone pair involved in forming coordinate bonds. And you also have polydentate ligands where you have a much bigger molecule and the metal ion is stuck in the middle, and lone pairs from all sides of the molecules are coming in and getting attracted to the metal ion. Is this clear? Anisha, clear? Saim?
Thank you.
Yes, sir.
And he's asking you to draw a complex ion that's, I mean, again, it's exactly the same thing. Whatever you've done in the notes, that's exactly the same thing. So you just have to. ये आवाज नहीं आ रही क्या हुआ? So that's one molecule. The N lone pairs from all sides. I mean, you can draw the lone pairs if you want to. Not really sure this is required, but I mean, obviously that's going to be correct still. So that's one version of the copper ion getting surrounded by, and this entire thing will have a charge of +2. Why? Because copper is +2, and this thing is neutral. So neutral things getting attracted to something that is +2, the overall thing would be +2. And bidentate ligands, they form optical isomers. So not what is optical isomers? Bidentate ligands, remember this, they form mirror images. When you have one bidentate ligand, there's going to be a mirrored version of the same molecule. So all you have to do over here is just draw the mirrored version. So the mirrored version would be that they're going to be connected together, and this thing would be on. So that's, now carefully draw the mirrored version, and that's going to be +2 as well. I mean, both of them will have exactly the same charges, but they're mirrored versions of each other. No matter how you rotate this, these are two non-superimposable structures, just like your two hands. Your two hands, they look very similar, but they are different in orientation. As I'm moving to the next one, again, this one, again, it's just a repetition of all that you've studied in the notes, which is given over here. Okay, it's ligand exchange. This is what we've studied. That copper is surrounded by water molecules. You add NH3, copper is now surrounded by NH3. If you add HCl, copper is now surrounded by Cl ions. So the ligand keeps changing. So you just have to use all of that. Write the formula of the following species. Which one? A. You add excess NH3, what happens? Copper is now surrounded by NH3. Either all of them, it's going to be completely surrounded by NH3. And because I think he's using excess NH3, so it would be safer to.
Yeah, that's true.
That it gets completely surrounded by NH3. Or you can add a bunch of water molecules as well into it. Like 2 water molecules, and but it doesn't really matter. The total combined number of ligands, they should come out to be 6. So even in the notes, the number of NH3 are variable. So just remember that there are 6 positions. So all 6 can be NH3s. And we can also. So over here he's using NH3 6. So that was my first hunch as well, because he's using an excess of NH3. If he had, but I still think this would be acceptable. But I guess he wanted to, I mean, the question wanted to, because he's using excess. But I'm pretty sure the examiner will correct this as well, because it's still aqueous. Even though it's excess, but it's aqueous, so there is water involved. Anyways, what is precipitate B? Precipitate B is, it's cobalt carbonate. So precipitate B is formed. So it's got to be cobalt carbonate. State is suitable reagent for reaction number 1, that's OH ion. So you can add NaOH aqueous.
Okay.
So, I mean, the water molecule is replaced by OH ions. Write an equation for reaction number 2. So you can do that. It's CO, H2O4, and OH twice. And you're adding NH3. So 6 NH3s are going to replace or displace all the the cobalt will now be surrounded by 6 NH3s. And the overall charge would be, I mean, for this, this would be +2. And what 4 water molecules and 2 OH ions are going to be displaced. So that's your equation for reaction number 2. And equation for reaction number 3 is going to be cobalt with 6 water molecules. And it has a charge of +2. It attracts the carbonate ion. And cobalt carbonate is going to be formed. That's going to be a solid, and the 6 water molecules. Now remember, once carbonate joins in, the overall thing becomes neutral. When it's neutral, it no longer attracts water molecules. So the water molecules that were initially sticking to it, why were the water molecules sticking to it? Because cobalt had a charge of +2. But once the carbonate gets attracted to the cobalt, it becomes neutral. So the water molecules are no longer sticking to it. Is that clear as well?
Yes, sir. Thank you.
And the same thing happened with OH ions as well, that once you add, like if you have copper and once the ligands, they get displaced by OH ion, the whole thing becomes neutral. So the water is no longer going to be attracted to it. So the water would leave. It's just going to be copper hydroxide. Now the next question is, okay, cobalt ions catalyze the oxidation of this thing to this thing and carbon dioxide, right? What property allows cobalt ions to act as catalyst? I'm pretty sure variable
Different
oxidation.
oxidation.
Yeah. So variable oxidation states. Because they're capable of gaining electrons, they're also capable of losing electrons. So unlike, like, for example, group 1 metals, they always lose electrons. Non-metals, they always gain electrons. But transition metals have this property that they can do both. So this one, 2, 3, you have to draw this ion. 2, 3, it's but, that means 4. Now, butane diode, that's butanoic acid. It's an ion of the butanoic acid, and it's dioate. So it means on both sides, there's going to be butane dioic acid, and the H+1 is left. And then there is 2, 3 hydroxy. So that means on the second one and the third one, there is OH as well. And you've got H atoms over here. As if I complete the equation for the oxidation of this thing, use O for the oxidizing agent. So we're going to use O. And what is it forming? Did he say what it's forming? He's saying to meth this thing. To methanoate ions, which is HCO2 - 1, and carbon dioxide and water. So this thing gets oxidized, and you can just balance the number of oxygens. That's so that's going to be, which thing should be?
So carbon dioxide क्यों produce होगा?
उसने कहा है, मैंने तो
कि ion produce हो रहा है.
नहीं, उसने कहा है कार्बन डाइऑक्साइड प्रोड्यूस हुआ. तो ये पूछ रहे कि रिएक्शन क्यों हो रहा है?
नहीं, मैं कह रहा हूँ ये प्रोडक्ट्स आपने रिएक्शंस में लिखे हुए HCO2 नेगेटिव, ये गिवन है कि ये
प्रोड्यूस होगा? गिवन, ये यहाँ पे उससे कहा है, मतलब we didn't make this equation, we didn't study this, ठीक है? So it's already given in the question. So all you have to do is balance it. Now that's going to be kind of problematic. So how do you balance this? It's as is the first thing. You're getting this thing, right? It's I'm just studying this. It's going to be I think there's going to be two of this and two of this. That is my hunch. And so that would make up for the 4 carbon atoms. Because if it gets oxidized, right? I mean, there are 2 ways of balancing, because you have to balance the number of electrons gained and lost. So my assumption is that you have 4 carbon atoms, right? So the ones at the ends will probably get oxidized into the same thing because it's symmetrical, right? So if this thing undergoes a certain amount of oxidation, which I don't know what's going to happen to it, but whatever happens to this one, the same thing happens to this one. So basically 2 of the carbons, and whatever happens to this carbon would also happen to this carbon because they're exactly identical. So that means, so my idea is that if you have this molecule, that's this molecule over here, 2 of the carbons will turn into a certain product and 2 of the carbons will turn into this other product. Is the idea clear? Because I don't know what reaction is happening. I have no idea what this is. But my hunch is that these 2 things would be present in equal proportion. These 2 carbons will turn into the same type of product, and these 2 at the ends will turn into the same type of product. So 2 of these and 2 of these would be produced. And now you can balance the hydrogens. That's 2 hydrogens over here. So so that's balanced. How many oxygens do you have? 4 plus 4 over here. That's 8. 8 plus 1. That's 9. So I think you need 3 oxygens. So this is completely random. I've just made an intelligent guess of what the reaction is. I'm just going to check the marking scheme now. So which one is this? It is the same thing. It's 3O. Remember, redox equations are pretty hard to balance. I mean, you have to use oxidation states. But over here, we avoided calculating the oxidation states. We just made an intelligent guess and we figured out what the product is going to be. Is this clear?
Yeah.
And cis and trans isomers of platin, which is cisplatin and transplatin, which I mean, you have to remember that one as well. So this is with cis and trans. 1 second. This one. So platinum ion is surrounded by 2 NH3s and 2 Cls. It's a square planar molecule, square planar complex. And there are going to be 2 versions of this. Either it's going to be cis, the Cls are together, or the Cls are at opposite ends. So in this question, you just have to draw both of them. One would be that the 2 NH3s would be together, and one would be the 2 NH3s and the 2 Cls are opposite to each other. And then he's talking about the anti-cancer. Describe the action of cisplatin in this role. So we did that as well, somewhere over here. What we did was that cisplatin was an anti-cancer drug. What I explained was that cancer is when your DNA degenerates or becomes damaged. So those cells should stop replicating. The DNA should stop replicating. So what cisplatin does is that for replication, the DNA has to unzip. It has to split. Just like a cell splitting. And what cisplatin does is it does not allow it to unzip, because 2 of the NH3s, they get replaced by the bases in the DNA strand. So that is what happens. Is that part clear? I mean, if you know biology, that would be much easier, but I did explain this in the, and you just need a general overview of this. Is this clear?
Yes, sir.
So the way that they have, where's their answer? Just a second. They've just given it in the most general way possible. They're not even talking about the bases. They're just saying that it can react or bind with the DNA, which prevents replication of the strand. That's it. So you don't really have to go into that much detail. It's just that, just remember that the platinum ion, 2 of the NH3s will get replaced by the DNA nitrogens, and the 2 strands would get locked by the platinum. So the platinum would be holding them together, And this would prevent the cell from splitting, and it will keep the DNA strands together. And so, okay. What's this question? Just a second, sorry.
Correct.
How kya hua? So this one is the use of cisplatin. That's last one. The use of cisplatin can cause the side effects of. So carboplatin has been developed. Now carboplatin can be synthesized from cisplatin by replacing the two chloride-ion ligands with a single cyclobutane. So here are the lone pairs. I mean, it's negative charge, right? So he's saying that. Now remember, this is cisplatin. So I'll just quickly do this. Cis means that the two NH3s, it's a square planar molecule complex. And here's your Cl and here's your other Cl. This is actually +2, this is -1, this is -1. So he has clearly stated that it replaces two of the chloride ions. Two of these are going to get replaced. So they're going to get replaced by what? By this molecule over here. And so I have to, so they're going to be replaced by this molecule, which is double bond O and O -1. Hopefully I've drawn that correctly. And this one as well, double bond O. So instead of the CLs, this thing, one of them has displaced both the CL lines. Suggests the structure. So we have drawn that in the box. That's the structure. And you write the overall charge. You don't write the individual charges. So don't mention charge over here. The overall charge would be 0. Because this was -1. This was -1 as well. This was +2 actually. So it's this one. So the overall charge is 0. And this is exactly the same thing that we've drawn. So is this clear? This question?
Yes, sir.
So here, let's continue.
Yes.
Sorry, let's continue tomorrow then.
Okay. Thank you.
Thank you, sir.
Okay, love.
Thank you.
Thank you.